Dear friends, Maths Aspirants is a community of mathematics students, research scholars, and teachers started by myself in 2017. We used to arrange online test series and online problem solving sessions. And as a part of that series, we have a session by Mr. Balasubramanian. As all of you know, TIFR GS 2023 examination is on December 11th. For those who prepare for that TIFR exams, this year we are arranging 3 online problem discussion sessions. Today is the first of that sessions. I'm very happy to introduce Mr. Balasubramanian. He is currently pursuing PhD at IIT Guwahati, and Balu did his M.Sc from Cochin University of Science and Technology, and he cleared CSIR JRF and joined for PhD, and now an SRF, Senior Research Fellow at IIT Guwahati. Mr. Balu is a member of Math Aspirants groups since his M.Sc times itself. I'm very happy and proud to introduce Balu to all of you. And also I express my gratitude to Balu for being with us. I hope that today's session will be really useful for the TIFR aspirants. I wish you all a vibrant academic time ahead. I welcome everyone to this program. Welcome, Balu.
Thanks for the introduction. Good morning, all. So I'm very happy to be part of this. I think I am taking this around 3rd or 4th time I am taking this class. Before, so I have been part of this. So thanks for calling me again for taking another class. So today we will be mainly solving problem. Let me come to the point. So today we will be mainly solving problems from analysis and linear algebra from TIFR. Mainly I have chosen questions from TIFR 2013 to 2019 and 20, at most 20. So we will be first dealing some questions from real analysis. Then we will be seeing some questions from linear algebra as well. So actually, the one thing I want to tell you, in the class, we will be mainly focusing on how to solve the problem, like what kind of approach we should use and all. So theory part we won't be discuss much. So that will be we will be recording things, the main theorems and also and notes, some facts. Those will be mentioned, but proof of those many items that we did during our M.Sc and did before, those won't be discussed much. So I am assuming that you know that those things. So we will be solving dealing with problems. So that's what all about. So let us begin then directly. First, we will be seeing some problem from analysis, as I said. So this is a question from TIFR. All the questions that I took is from TIFR only. So let us begin with this question. As I said earlier, it will be mainly oriented like problem solving oriented. So yeah, well, let's start. So the question is that we are given 2 sequences, sequence n and bn, of real numbers such that series n square and series bn square are convergent. Then what can we say about the series n bn? Whether it is absolutely convergent or may not convergent or always convergent, but may not converge absolutely, and it converges to 0. And coming to the solution. So what do you think? Do anyone know what do you think the answer? Whether it is convergent or not? Anyone knows how to approach this? So let me tell you before that. Yeah, it is.
Yeah, my guess is absolutely using AMGM inequality.
Yes, exactly. That's a trick. We need to use AMGM inequality here. Yeah. So, yeah, you are right. You got the thing. Anyway, I'm solving this. So, for showing that it is absolutely convergent, we need to check whether the series mode A and mode Bn, which means mode of A and Bn. is convergent or not. This is what we need to check. This means series mod and Bn. So if you see, you are given two other series which are convergent. The general time of those series are of the form an square and bn square. So here you are checking the convergence of a series whose general time is modulus of a and bn. So first you think that whether you will be able to write this mod a and bn in some form of this a square bn square. So eventually we will have to use the fact that a square, series a square and series bn square is convergent. So you need to think in that way. Try to write mod a and bn in the form of n square and bn square. So that you see now, how can we write n mod n bn is nothing but square root of mod n square mod bn square, isn't it? Now see, this is a geometric mean of two numbers, real numbers, mod n square and mod bn square. Two numbers. See, you know that geometric mean is always less than or equal to arithmetic mean. So using this fact, this is geometric mean of these two numbers. This will be less than or equal to arithmetic mean of these numbers, which means modulus of n square plus modulus of bn square all divided by 2, isn't it? Now think. Now if I consider series, consider the series whose general time is mod n square plus mod bn square whole divided by 2. This is nothing but sum of these two series, mod n square whole divided by 2 plus mod bn square whole divided by 2. But we know already that this series is convergent. So if you are multiplying this series with a scalar number 1 by 2, that will be again convergent. The same way this series with some scalar like here 1 by 2, that is again convergent. So what we have got is that we have written the general time of a series mod n bn, general time this time less than or equal to series. This is for all n. So since this series is convergent, by comparison test we can say that then by comparison test we can say that series mod a bn is convergent. So which means what? If series mod a and bn is convergent, that means that series is absolutely convergent. So our option is true. So fine. I hope it is clear. This is one of easy question. Let's start with an easy question. Any doubt? I hope there is no hard doubt.
Sir, if we take an example, an equals to 1 by n and bn equals to minus 1 to the power whole by n, then
n equal to 1 by n, bn equal to minus 1 to the power?
Minus 1 to the power n.
Power n. Are you meaning this series? Do you mean this series?
Yes. No, sir.
Yeah.
bn equals to minus 1 to the power n only. By n, no.
Oh, bn equal to minus 1 to the power n. Okay, fine. Yeah. So if you take bn to be minus 1 to the power n, will this be convergent? Series mod bn, series bn square will be nothing but one itself. Series whose time is 1, whose general time is 1 will not be convergent, right? You got? Yeah. So that's the problem. We need to take a series a and bn sequence such that corresponding these series are convergent. If you take bn to be minus 1 to the power n, this series won't be convergent. We need to get a n bn such that this is convergent. Fine. Okay. Yeah. Question 2. This is another question from TIFR. So it's kind of interesting. So if you see, the question is that you are given a sequence and a sequence of real numbers such that mod n plus 1 minus n is less than or equal to n square divided by 2 to the power n for all n belongs to natural number. Question is to check whether the sequence is the option A, sequence n may be unbounded. Option B, sequence is bounded but may not converge. C, sequence has exactly 2 limit points, which means that time sequence will be not convergent, will not be convergent. The option, sequence is convergent. So how to approach this? Do anyone know? Does anyone know?
Both side taking summation.
Sorry?
But if given equation, both side taking summation.
Summation? Okay.
Okay. Then
What do you mean? Till we have this for n. You need to check whether this is convergent or not, or bounded or not. See, someone was saying something about, yeah, option A. He's saying option A.
I think, I mean, for an is equal to root n.
Maybe unbounded. Why do you think so? Any example?
Yeah, an is equal to root n, but I have to check
N equal to root n. If you take n to be root n, will you get this this kind of relation?
Yeah, that's what I am solving.
Yeah. So please check it.
Will it be
You
true
can
for
check
this
it. So if you take n to be root n, usually you will not be getting this thing. You won't be able to bound root n plus 1 minus root n is less than or equal to some n square divided by 2 to the power n for all n. Just please check it. Also, this sequence is first of all divergent and unbounded as well. Please check it. The trick is to look at this thing. See, this time is we are given a bound. We are given that mod a n plus 1 minus n less than or equal to n square divided by 2 to the power n, right, for n. See, this time is an actually general time of a convergent series, isn't it? If you consider series, the series n square divided by 2 to the power n is convergent, isn't it? Just use ratio test or root test.
Yes, sir.
Yeah. So you are given a general time of a convergent series. Yeah, root test and ratio test will also work. So they could have given some 1 by n. So if you take a series with 1 by n, that won't be convergent. But instead of that, they have given a series whose general time is convergent. So you may need to use some sort of series thing like, so series things, whether convergence of series and all. So that intuition you should develop in the very beginning. Given as some particular form, you can show that this is, since it is convergent, n squared by 2 to the power n goes to 0 as n tending to infinity. If it was 1 by n also, it would have gone to 0, but the rate is not that much as n by 2 to the power n goes to 0. So this you need to make use of. Please remember, this is kind of intuition, and that we can relate this with a series. That kind of intuition you are getting from this. Now coming to the problem, actually, see, how can you prove a sequence of real number is convergent? What are the ways to prove? If you are given some sequence of real numbers, how can you prove that, whether or not? I'm only asking for convergence now. Anyone?
Yeah, so we can show it It is Cauchy. We can
Yes,
prove that
exactly.
it is
That is the one of the
Cauchy.
easiest way. If you are Cauchy for showing convergence, we don't need to find the limit. If you are able to show that sequence of real number is Cauchy, that will automatically become a convergence series. So that is a trick. But other methods are like you need to find limit and you need to show epsilon data definition. For any epsilon greater than 0, there is a natural number n naught such that mod n minus L is less than epsilon 4 or n greater than or equal to n naught. That is another one. Other method like if a sequence is monotonically increasing and bounded, then it will be convergent, and a monotonic sequence which is bounded is convergent. But here it doesn't look like it will be able to shown it is monotone or bounded, just monotone. So these are the way. So simplest way is, if you are not having anything, simplest way is to show Cauchy. Also you can see this kind of relation an plus 1 divided by an. You can relate. You will be able to relate it with mod a minus a by just triangular inequality. Those kind of intuition will lead you to using this trick Cauchy sequence. So we are going to show that this sequence is Cauchy using this idea. This much we are having. So using a number, let m n belongs to and m greater than small n. When I'm estimating this value mod n minus m minus an, this I can get modulus of am minus a m minus 1 plus a m minus 1 minus a m minus 2 plus etc. plus I'm writing final 10 plus last time will be a n plus 1 minus n plus 1 minus an. The second last time will be a n plus 2 minus a n plus 1. Isn't it? Is it fine? After cancellation, I will be left with the mod m minus n. So by triangular inequality, I can write this as mod am minus a n minus 1 less than or equal to, club this all these two times, then you will be getting this is a plus modulus of a m minus 1 minus a m minus 2 plus etc. plus modulus of a n plus 1 minus l. So now we can apply the thing that we are having. What we are having is that it's less than or equal to n to the n squared divided by 2 to the power n. So this is less than or equal to a minus 1 square divided by 2 to the power a minus 1 plus etc. plus n squared divided by 2 to the power n. Isn't it? Now, wait. Now, this we are having. Let it be 1. Any doubt until now? So, since series n squared divided by 2 to the power n is convergent, its sequence of partial sum. What is the definition of convergence of series? If you're considering sequence of partial sum, series m equal to 1 to n, n squared m squared divided by 2 to the power m is convergent. So sequence of partial sum is convergent, which means if the sequence is convergent, it will be Cauchy as well. So sequence xn is Cauchy again, Cauchy as well. So what can we do then? Then Now I'm taking an epsilon. But what I have to show is that mod n minus sequence n is Cauchy. But now I'm almost done. But now I'm using the fact that sequence Sn is Cauchy, I'm going to show that mod n is n Cauchy. Now, but before that, you note that a minus an that we estimated to be this quantity, but this quantity is nothing but modulus of S m minus 1 minus S n minus 1. Please verify. Sn is to be this. Sn is sum of the first n times of this series. Then mod n minus a minus n is nothing but this. So now what? Now let epsilon greater than 0 be given. Then since xn is Cauchy, there exists some capital N such that not capital, I'm writing n naught such that modulus of Sn minus Sn less than epsilon for or n m greater than or equal to n naught, since Sn is Cauchy. Okay. So now choose let capital N to be n naught plus 1. Then what we will get, mod am minus n is less than epsilon for or n m greater than or equal to capital N. See, it follows from this. I'm taking capital N to be n naught plus 1. So which means we have just done an epsilon and we have found a natural number n such that mod m minus n is less than epsilon for or n greater than or equal to capital N. Now remember that we have assumed m greater than n. You can do the same thing when m greater than m also. So without loss of generality, we can choose in the beginning itself like this. So proof is same. There is no change in proof. So which means we have shown that sequence n is Cauchy implies n is convergent. So this is the fact of series and all we have shown this is convergent, which means yes. Any doubt?
Sir, why we are not applying here simply this n square upon 2 and tends to 0 when n tends to infinity. So
Yes,
this
yes,
an
yeah.
is convergent. Why we are not applying?
Yeah, you are saying we are not using the fact that e to the power n divided by 2 to the power n goes to 0.
Yes, sir.
Are you asking this?
Yes, sir.
Hello?
Yes, sir.
Yeah. Actually, this itself is not enough. That's a thing. See, if as I said, you will be able to find out a sequence which satisfies this condition n minus m, which is less than or equal to some another sequence bn. For example, maybe 1 by n, or it did not be 1 by n like bn, but this bn goes to 0, but this n doesn't converge to 0. For example, if I take someone said n equal to square root of n. If you find out for that n plus 1 minus n, you will be getting square root of n plus 1 minus square root of n. This you can multiply by numerator and denominator by square root of n plus 1 divided by n plus 1. Then finally you can show that this is going to 0. This is bounded by a convergent sequence, which is going to 0. So in that case, but n is not convergent. Is it fine?
Yes, sir.
Yeah. If you are taking n to be like this, you will be getting, if you are taking n to be like this, you will be getting this is less than or equal to this kind of sequence. So you are getting another sequence RHS, but this sequence will go to 0. That you can show. Just multiply numerator and denominator by square root of n plus x1 plus square root of n. Then you can see that this goes to 0. So somehow we need to you need a stronger sequence in the sense that that sequence goes to 0 somewhat fast, in the sense that if you are constructing his whose general time is that sequence, then that series should be convergent. So we need to have that kind of sequence. Is it clear? Only
Yes, sir.
this
Thank
sequence
you.
goes to 0 is not enough. Yeah.
Okay, sir. Okay.
So system. Question 3. Well, so this is a question from uniform continuity. Uniform continuity, you can expect questions in many exams, not only in TIFR and net examination mainly. There you will always encounter questions related to uniform continuity. This kind of important topic. You should be you should know the concept very clearly about uniform continuity. You will face the question in many areas. Not just definition. You should know. You should have a lot of examples in your hand and techniques. If there are different methods of showing uniform continuity, like in border interval, if unbordered interval. So, but here we are using some different techniques. So, first you are given a function f from R to interval 0 to infinity, be a continuous function such that gx is equal to f of x all square. That is uniformly continuous. You are given a function f whose square is uniformly continuous. Then question is that which of the following statements is always true? Option A, f is bounded. Option B, f may not be uniformly continuous. Option C, f is uniformly continuous, and option D, f is unbounded. So, does anyone know? What do you think? Whether it will be uniformly continuous, whether f will be uniformly continuous or not?
Option B, sir.
Option D, f is unbounded. Or
B, sir. B, second option.
B, it may not be uniformly continuous. Are you having any example?
Fx, if I take identity x, fx equal to x.
F of x is equal to x. Then gx will be what? X square. Is x square uniformly continuous? Is x square uniformly continuous?
No, sir.
No, right. Please verify. Square is not uniformly continuous. You can find. You can show me like you can using sequence. You can show if you're taking some like previous example. We saw a sequence. If you are taking a sequence like this, xn to be square root of n plus 1, yn to be square root of n, then modulus of, this is another criteria, xn minus will goes to 0, but modulus of f of xn minus f of yn will be always equal to here what? This many of you may be knowing, but this is a trick. Like if you are able to find, this is one trick. Trick is that if you are able to find a two sequence x and y which converges to 0, but if you are considering a corresponding sequence f of xn minus f of yn which is always greater than a fixed positive number, then you can show that that function is not uniformly continuous just by using the definition. I'm not going to prove. Please, in general, I say the statement. Please try to prove that statement. If you're able to find out a sequence, like this need not be so. If you are able to show this is greater than some fixed number for a greater than 0, 4 or n, this is enough. If you are able to show these two things, then you can show that function is f is not uniformly continuous. Please prove this. I'm not proving by using the definition of uniformly continuity. Yeah, this is one of the simple methods. This method will be useful for many problems. For getting some sequence, it is all about choosing a right sequence. Yeah. So, anyone, whether it will be uniformly continuous? Can it be uniformly continuous? Any example? Can we show that it is uniformly continuous? The thing is that here we can show this using just 2 steps. If you are getting that idea, if you know that concept, you will get the answer immediately.
If fx is bounded,
if fx is bounded, it is, you are saying it is uniformly continuous, right? Is it?
yes.
But if you are taking fx to be square root of x, gx will be equal to x, but fx is not bounded. Square root of x function is uniformly continuous, and gx is also uniformly continuous.
I'm
Yeah.
saying
Okay.
if you assume fx is bounded, then
Yeah. Sorry. Yeah. Then in that case, fx is bounded.
yeah, because product of uniformly
Yeah.
continuous function is uniformly if it is bounded, right? Both are.
Yeah, in
Bounded.
some sense you can say that you will be able to, but it is not bounded. Remember that f of x is equal to x. If fx is
Yeah.
that
is okay.
That need not be. I think I can choose function gx. How will you show that fx is bounded? It is uniformly continuous. Piecewise function. I'm asking how will you show? Any idea? Okay. I'm coming to the problem. Actually, you can show that this is uniformly continuous. Please try to find a counterexample. I will be seeing if its boundedness will matter or not. If will not be bounded, actually, like as I said, this option is definitely false. If you are taking fx to be square root of x, this will be cancelled, and it may not be uniformly continuous. And also, we will be showing f is uniformly continuous. So f is unbounded. That is also not necessarily true. If you are taking fx to be some constant function, this will do the job. So things that f of x square is uniformly continuous. This is uniformly continuous. You know that square root of function, the function gx, if you are sub hx, square root of x is uniformly continuous. Now let me know, if you are having a two function f and g, will the composition of those functions f composition g, will it be uniformly continuous? Let if
Yes, I guess.
yes, right.
Yes, sir.
If you don't know, please prove it. If h1 and h2 are uniformly continuous, then h1 composition h2 will be uniformly continuous. So here, square root of x is uniformly continuous and f of x square is uniformly continuous. Then gx equal to fx is nothing but square root of x composition f of x whole square, which means square root of f of x square. That means we have written f of x whole square is already uniformly continuous, square root of x is already uniformly continuous. If you don't know, please prove it. A square root of function, it is a uniformly continuous function. For that, I'm just writing the definition as well. What is the definition of uniformly continuous? For for any epsilon greater than 0, there exists delta greater than 0 such that modulus of f of x minus f of y less than epsilon for or n greater than or equal to for mod x minus 1 less than or equal to delta, less than or equal. So this is the definition. So using this, you can show that composition of two uniformly continuous function is uniformly continuous and square root of x is uniformly continuous. And giving a hint, there are many methods. One method for epsilon, if you try to choose delta to be equal to epsilon square, that is the one trick. You need to use some inequality as well. You might have done in your class. So our f of x is nothing but composition of the uniformly continuous function. So f is uniformly continuous, since composition of the uniformly continuous is uniformly continuous function. Is it fine? Boundedness is not playing much role. Even if f is unbounded, it continues. But of course, yeah, someone said if f is bounded, it will be uniformly continuous. Actually, that is true only, since here not only when f is bounded, cases here f is uniformly continuous. Remember that. So no need of searching for counterexample. It is already uniformly continuous. But unbounded case also it is uniformly continuous. As I said, square root of x. Okay, I hope it is clear. Yeah. Let us come to a question related to derivative. So the question is that you are given a sequence, no, you are given a differentiable function f from R to R, such that limit extending to infinity f of x, f dash of x equal to 1. Then question is whether f is bounded, f is increasing, f is unbounded, then f dash is bounded. So what do you think? First, this kind of thing, first try to use some intuition. You may not be able to say the answer by theoretical thing immediately, but will you be able to get some intuition about bound of f using this? Like derivative of f is going to 1 as extending to infinity. By that intuition, will you be able to say something? You need to have that kind of intuition.
Sir, can we say f dash is bounded?
We cannot say f dash is bounded.
Sir, if we take f of x is equals to x, then a option is discard.
Yes, of course, yeah. If you are taking f is equal to x, a option is discard. Will f be unbounded always?
Hello.
Yeah.
Yeah. If I choose fx equal to e to the power minus x plus x.
Fx equal to
e to the power minus x plus x.
e to the power minus x plus x.
No, no.
Sorry, sir. No. Yeah. Go. Yeah.
Plus x.
Yeah.
Then option B can be discarded.
E to the power of minus 6 divided by minus, then 1. Derivative will be equal to e to the power minus 6 minus plus 1. 1 minus this. This is
0.
1 minus e to the power minus 6, right?
Yeah. So this term goes to 0 at plus infinity, and we have 1.
Yeah. This was zero. Yes. This was to one. Yeah.
So with this
Yeah, yeah.
example, I think option A and B both can be removed.
A and
A
B.
and B, yeah. I mean, fx equal to
Yeah.
x also works, but then
Yeah. Yes, yes. Yeah, okay, fine. Here actually you're getting e to the power -6. This yeah, sometimes f dash is positive or sometimes f dash is negative. So it is not increasing always.
Yes, yes.
Yeah. Yeah. You can remove like this, you can remove A and you can remove B and you can remove even this also by choosing example.
Yeah, then C is the only.
Yeah. Yeah. C is the only possible. Yeah, I got, yeah. C should be the answer. Yeah, by removing eliminating by choosing some example, you can remove some option, you can find the answer. But are you getting and if question is like show that this is this, like if it's a true or false question in TIFR, you will be getting question true or false as well. But anyway, whatever be the question, you should be always aware of how to find out the solution, how to prove this. So answer is F is unbounded. So also other notion, we will be proving that. But before that, I'm trying to give you some intuition. See what happens. Yeah, go ahead.
Sir,
Yeah, one intuition might be like we don't know what happens at -infinity with both the function f and f derivative.
Yeah.
So that can be our motivation to come up with an unbounded math. Yeah.
Yes.
Sir,
actually, this f dash can be. Sorry.
Sir, can we use the definition of limit?
Yeah, definitely.
Mod of f minus 1 is less than epsilon. Sir, we are taking epsilon greater than
minus 1 less than epsilon.
Less than epsilon, okay. For all mod x greater than delta.
Not mod x, for all x greater than delta. You cannot say because it is you are saying x into plus infinity as well only. This you can say for some delta greater than 0. Yeah.
And then if I write that mod fx minus 1, then it will be 1 minus epsilon less than f dash x less than 1 plus epsilon.
Mod fx is less than
1 minus epsilon 1 minus epsilon less than f dash x less than 1 plus epsilon.
1 minus less than 1 minus less than epsilon less than. Are you saying something like
not
this?
Mod f.
I
am saying that we can write mod of fx minus 1 as between minus epsilon and epsilon.
But see, but here you are having f dash, right? Modulus of f dash minus 1,
yes,
that's only thing. Yeah.
Sir, 1 minus epsilon is less than f dash x minus less than 1 plus epsilon.
Oh, you are writing this. Okay, got it. You mean that 1 minus epsilon less than f dash of x less than 1 plus epsilon. Okay, yeah. This is possible when x greater than delta. Then,
yes, sir. Then if we integrate it.
Then integrate from what number to what number?
0 to x.
0 to x. Okay, 0 to x. 1 minus epsilon to the dx less than integral 0 to x f dash of x dx less than 1 plus epsilon integral 0 to x. Okay, fine.
Yeah, my doubt is this how do I know that? So this inequality we know after some delta, right? So
yeah, that's the thing. So that's what I said.
Integrate.
Yes. This is the thing. This is only possible. You cannot use this. Sorry, I wrote here less than. you cannot write this less than, because this is possible. This inequality is valid only after when x is greater than delta. I think if you're choosing something like here delta, you can write here if you are choosing delta.
Yeah.
Now this is clear. Now you can, I think this tool will do the job, I think. 1 minus epsilon into x minus delta. That's what you are getting. Only focus on these two things. Here what you are getting, which is less than, by fundamental theorem of calculus, this is, you can write f of x minus f of delta, isn't it?
Yes, sir.
Yeah. But you can see f of delta is a fixed number, delta is a fixed number, epsilon is a fixed number. As x tending to infinity, what will happen? This time will go to say infinity. 1 minus delta, sorry, if you are taking limit on both sides, limit x tending to infinity, this time goes to infinity. Limit of 1 minus epsilon into x minus delta equal to infinity. So which means this time is unbounded. Which implies fx minus f of delta goes to infinity as x tending to infinity. Then this time zone LHS is unbounded, which means this time zone RHS will be unbounded. What I am getting is that this time 1 minus delta, 1 minus epsilon to x minus delta is unbounded, implies fx minus f of delta is unbounded. So see, f of delta is a fixed number. So then fx should be unbounded. Please, please, there are small things. Please verify all these things. Convince yourself. Fx is unbounded. Is it fine? If fx is, thinks that if fx is bounded, this time this will get bounded. See, if x is, that's a trick. So actually, this is a right solution. It's fine. It's a nice solution as well. Using integral, we have used the idea from calculus, fundamental theorem of calculus. If a function, you're having a function f dash integral of delta to x, f dash of x is nothing but fx minus f of delta. So by this you can say that f is unbounded. Actually, I did not thought of this solution in the beginning, but it's a nice solution. Good. So is it fine, this solution? Any doubt? The thing is here you have to use this fact. The first problem that we made is that we started 0. We tried to 0. So, but this is only we are having you can choose this delta to be 1 less than 1. Choose delta less than 1, like delta to be 1 by 2. The reason is that I'm saying, otherwise what will happen if delta is greater than 1, this quantity will become negative. So if this is becoming negative, as x tending to infinity, this is going to negative infinity. So in order to avoid that case, choose delta to be less than 1, in particular 1 by 2 will do the job. Then you can show that this bottom lower function is going to infinity. That means that function is unbounded. So we can say RHS function fx minus f of delta, that is also unbounded. So that's the thing. So trick is to choose delta, lower bound to be delta. Yeah, this is one thing. So I want to give one more solution as well. Solution that I thought that is used. This solution is using idea from calculus, fundamental theorem of calculus and all. So we can do this using Gnewald theorem as well. So I'm giving a proof using a Gnewald theorem. Before that, I'm giving a kind of intuition behind saying this is unbounded. See, here what happens is that as x is becoming larger and large, f dash is approaching to 1. That means f dash is, you can say that f dash is becoming almost like 1. The derivative rate of change of function is almost becoming 1, which means the function is having some sort of increase. Like when x is large, when there is 1 unit of change in x direction, we are getting a 1 unit change in y direction. Derivative means what? Rate is a rate of change. So rate of change is somewhat stable only, like somewhat greater than some fixed number. So in that case, you can have kind of intuition that f is unbounded. That is one thing. By that, then for proving that, you need to use some theoretical techniques. So this is one of the things. So it's nice solution. And another solution I'm giving using Vinod theorem. Solution 2. See, you can, given limit x tending to infinity plus infinity, f dash of x equal to 1. Then I can find then there exists what? There exists x naught belongs to R such that for all x greater than or equal to x naught, f dash of x will be greater than or equal to 1/2. Please, this is coming from the definition. If you are taking delta to be by definition, what does this mean? For any epsilon greater than 0, there exists x naught such that modulus of f dash of x minus 1 less than epsilon for all x greater than or equal to x naught. This is what the definition of saying limit x tending to infinity f dash of x is equal to 1. So if you choose delta to 1/2, if you are choosing delta to be 1/2, after simplifying this absolute value sign as we did here, we broke the absolute value symbol like this. Same trick will take you to f dash of x is greater than 1/2 for all x greater than or equal to x naught. So I hope this is fine. Please verify. So now see, if it's a differentiable function, then I'm choosing let x greater than x naught. Now by Minoy theorem, can I write this something? Can I write this in some way? F of x minus f of x naught divided by x minus x naught. This is equal to f dash of y for some y belongs to x naught x by Minoy theorem. Is it fine? Right? If it's a differentiable function, it is a continuous function. If you are fixing an interval x naught x, you can have Minoy theorem. You can apply the Minoy theorem of the function in that interval. Then you will be getting a y in the point x naught and x such that f of x minus f of x naught divided by x minus x naught is equal to f dash of y for some y in between the point x naught and x. Now see, this y is coming from this interval. Like if you're having this is x naught, this x, y is coming from somewhere here in the middle or some point in between x naught and x. So
can you explain the last line again?
This Minoy theorem.
Okay. There exists x naught. Yeah, there exists x naught. Then for every x bigger than, then we have f dash x is bigger than half.
You are asking that?
Yes. So this half is your epsilon, right? Yes.
Yeah,
so
I'm taking
this half is your epsilon.
Yes. If you are choosing take
Okay.
epsilon to be half in this definition. You will be getting corresponding to that epsilon, you will be getting an x0. I'm taking that x0. I'll break this absolute value thing into a f dash of x is lies between 1 minus epsilon and 1 plus epsilon. So f dash of x is always greater than 1 minus epsilon. If you're taking epsilon to be half, it is greater than 1 by 2. Yeah. Well.
Yeah.
So
it's fine.
Okay. So what will happen now? See, if f is bounded, now we are trying to bring a contradiction by assuming that f is bounded. Assume that f is bounded, which means what? There exists m greater than 0 such that modulus of f of x less than m for all x. So if that is the case, I'm going from number 1. That is the case from 1. What we get is that f dash of y, modulus of f dash of y is nothing but modulus of f of x minus f of x0, the whole divided by x minus x0, which is less than or equal to modulus of f of x minus f of x0, not less than, it is equal to as well, divided by modulus of x minus x0. By triangular inequality, I can write this is less than or equal to, only I am applying triangular inequality in the numerator, f of x plus modulus of minus of f of x0, which is less than or equal to divided by what? X minus x0. But this is less than or equal to, f of x is less than or equal to m for our x. So in particular, this is less than or equal to m plus m, they all divided by what? X minus x0, which means I'm getting some 2m divided by what? X minus x0. Is it fine? Now what you have got is that for x greater than x0, modulus of f dash of y less than or equal to 2 divided by x minus x0. Now see, this y is coming from y belongs to x0 and x. But whenever y is in x0 and x, modulus of f dash of y is always greater than 1 by 2. Note that. And see, this function is bounded by a function 2m divided by mod x minus x0. But limit x tending to infinity, 2m divided by x minus x0, this mod, or I'm taking x to be positive, so no need of taking mod also. This goes to 0. Please, groups, the water function is going to infinity. So like 1 by x is like the function 1 by x is going to 0 as x tending to infinity, which means f dash of y goes to 0 as x tending to infinity, because y is always a number in between x0 and x. But this is not possible because f dash of y is always greater than 1 by 2, since y is coming from the interval x0 since y is greater than x0. This is a contradiction. This is said as f dash of y greater than 1 by 2 for or y greater than or equal to x0. So is it fine? This, in a doubt, this we did by Vinod theorem. We got actually two different solutions. One is using calculus, other one is using Vinod theorem. Is it fine? Any doubt? Hello?
Fine, sir.
Yeah.
Yes, it's fine.
Yeah. So answer is f is unbounded. trick is to choose this x0 in both sides. In both problem we choose here. We request to choose this delta as well. Here we choose some x0. Somehow we have to use the definition that f dash of x is going to 1 as x infinity. Yeah. Now coming to the next problem. Read this question. Just a second. 10 seconds. Yeah, well, you are given a function. You are given a function f which is continuous on close and double 0 1, and then what is the limit? Limit n tending to infinity integral 0 to 1 n into x to the power n f of x dx. F of 0, f of 1, supreme of x, f of x, where x varies from interval 0 to 1. The limit does not exist. So, what do you think? What will be the limit of this function? Anyone? Do anyone know? Does anyone know?
Sir, we can take the limit inside of the integral because f will be uniformly.
Is it possible? Can we take limit inside integral? Those kind of things are, if it is, those things are possible, like plurality uniform convergence. If you are having a sequence of functions which are uniformly convergent to a function, other function, then you can take limit inside. Is it allowed here? Is it always possible?
Sir, this function will be uniformly continuous.
Which function? Oh, okay. Yeah, f function will be uniformly continuous. Okay. This function will be uniformly continuous. But taking limit inside, is that there you are using uniform convergence, right? Are you saying this that? Yeah. If fn converges to f uniformly, then integral fn limit of integral is nothing but integral of f. That means we are taking limit inside. But here you are having only uniform continuity. You are not having anything such as such uniform convergence.
Okay, sir.
Yeah. Well, any ideas? But you can discard, as like previously, you can discard the options and all. Those are like only for examination, but after that you need to do the actual solution also. So you can discard, if you choose some function, you can discard many things. Like f of 0, you may be able to discard limit does not exist. That also you can discard. Supreme also, I think you will be able to discard. I'm not going to any particular example.
Sir, by taking f of x is equals to x, we can discard option A and C also and D also.
A, C, and D. F of x is equal to?
F of x is equals to x. We can
X.
discard the option.
Then what you are getting, you are getting the integral to be integral 0 to 1 in x to the power n f of x. Dx is nothing but integral n into 0 to 1 x to the power n plus 1 the whole divided by n plus 1, isn't it? Then this is nothing but n into 1 by n plus 1. But this goes to 1.
N plus 2, right?
Oh, sorry, n plus 1, n is plus 2. Sorry. So
after
here it's plus. Okay, got it. Yeah. N plus 2 you are getting. N plus 2 divided by N plus 2. Here you will be getting N plus 2.
I can see only option A can be discarded. How C? Because the limit is 1 and supremum
Yes,
is
yes,
also
I
1.
got it. Yes, I got it.
Yeah.
After I say, I
Yeah.
think that thing.
So you can say option A and B, but from that also you will be able to do some example. Like if you are choosing function to be -6, it will be fine. If you are looking f of x to be -6, then I think you will be able to show that this limit, no, that time the limit will be going to I'm saying take the f of x to be some x plus 1. Oh, then also it is a problem.
No, we can take constant function 2.
Yes.
Then option B.
Constant function. Constant function won't be. I'm taking. Okay, well. Choose f of x to be -6. Then you can show that this limit into x to the power n f of x goes to -1, I think. Yeah, -1. But that is not the supremum of this function on the interval 0, 1. Please verify this.
Yes.
Yeah. So anyway, answer, you will be able to find out the answer in many ways by choosing some example and all. But that is the main idea is not that. The answer is you can show this f of x b. This limit will be always equal to b by doing something. But thing is to find how to show that. That will be needed for your other examination and interviews. That is a no. So how can you show that this limit is equal to f of 1? Hello? Yeah.
I have a doubt. If I choose fx equal to constant function 2.
Yeah. Okay.
Then the integral goes to 2, right? The limit of integral goes to 2.
Yes. Yes. Yeah. Limit of integral goes to 0.
Yeah. Sorry.
But that is itself again f of 1.
I'm wrong.
Yeah, it's fine.
Yeah, I'm wrong.
Yeah. So this is somewhat tricky. See, look at this time. You are having this time. You need to find out the limit of this time. Integral 0 to 1 n x to the power n f of x dx. So can you write this in some other form? Like, can I write this is equal to integral 0 to 1 n into x to the power n f of x minus f of 1 dx plus n into n plus 1 into f of 1? Can I write this? Please verify this. Please.
Yes.
Yeah, I can write like this. If you're expanding this second time, you will be getting first time minus n divided by n plus 1 into f of 1. So this you are having. So now see, this time is going to, this is going to what? Yeah, this is going to f of 1.
Yeah, so now you will be using the continuity at 1, right?
Yes, exactly. Now I will be using the continuity of 0. Yeah. So because I need to use somewhat modular continuity of 1, I need to use something like f of x minus f of 1. Okay. So this is what we are using on the definition of continuity. So I need to use something like this. So for that, I wanted to bring these two terms together. So I wrote our function in somewhat a different form in such a way that I'm having this kind of form. by new form. So now see, the given thing is sum of two different things, and this one is going to f of 1. If I am able to show that this is going to 0, I can show that limit of integral 0 to 1 n into x to the power n f of x dx equal to nothing but f of 1, because this already we know this is going to 0, this is going to f of 1. If you are able to show that this is going to 0, I can say that this limit is nothing but f of 1. So our aim is to show that it is enough to show that this limit of this quantity is equal to 0 by using whatever things that we are having. Okay, well. So now consider this time, only we are focusing on the second time. Now to show that integral 0 to n 0 to 1 limit n x to the power n f of x minus f of 1 dx equal to 0. So you know f is a continuous function on closed interval 0 1. So in particular, every continuous function on a closed interval 0, every function in a continuous function on a closed interval is always bounded. So you can say that f is bounded on closed interval 0 1. Since f is continuous on 0 1, continuous function on a compact set is bounded. In other ways, f is bounded, so there exists m greater than 0 such that modulus of f of x is always less than or equal to m for all x belongs to 0 1. This we are having. Now other thing is that f is of this function is continuous on 0 1. In particular, it is continuous at the point 1. Since f is continuous at 1, there exists a such that a greater than 0 and a less than 1. That means a very close to the number 1. In particular, f of modulus of, let epsilon greater than 0. I'm taking a function. I'm taking a positive real number epsilon greater than 0. So corresponding to that epsilon, I will be getting a real number a such that modulus of f of x minus f of 1 will be less than for all whenever for x greater than a less than x less than 1. I haven't written the full definition of continuity. In particular, what you will be getting for this epsilon greater than 0, you will be getting a delta such that modulus of f of x minus f of 1 less than epsilon whenever mod x minus 1 less than delta, which means x is greater than 1 minus delta. So I am choosing that 1 minus delta to be a. Is it clear? In epsilon delta definition, choose a equal to 1 minus delta. I haven't written fully, I have said it in words. Since it's fine, you will be able to find some a in this interval 0 1, this a. After this, during this part, in this part, f of x minus f of 1 will be less than delta. Less than, I am writing less than delta by 2. This is also possible by continuity of f at 1. Is it okay? Any doubts?
Okay, sir.
Yeah. So well, now our integral is integral 0 to 1 n into x to the power n f of x minus f of 1. I'm taking absolute value. This is less than or equal to, this is equal to absolute value of integral 0 to a n into x to the power n f of x minus f of 1 dx plus integral a to 1 n into x to the power n f of x minus f of 1 dx, absolute value. So now, but this is less than or equal to integral n into integral 0 to, I'm applying triangular inequality. Triangular inequality as well as I'm taking absolute value inside integral. F of x minus f of 1. I'm doing two things together. Plus n into integral a to 1 x to the power n modulus of f of x minus f of 1 dx. Now, in this part, use the fact that f is bounded. In this part, use the fact that modulus of f of x minus f of 1 is less than epsilon by 2. Then integrating, this is less than or equal to, this quantity you can show that modulus of f of x minus f of 1 is less than 2m. That you can show. This quantity is less than or equal to 2m, since f is less than, modulus of f is less than m, by using triangular inequality. Here you can write 2m into n of integral 0 to a x to the power n dx plus, here you can write epsilon by 2 into n integral 0 to 1, not 0, a to 1. A to, this is a to 1 x to the power n dx. Now it is almost done. Now this is nothing but 2m n into x to the power, I'm writing in one step, I think a to the power n plus 1, the whole divided by n plus 1 plus epsilon by 2 into, here you will be getting n into s to 1 minus a to the power n, a to the power n plus 1. Is it fine? Please verify these combinations. So this I can again see, a is a number which is less than 1. Then a to the power n plus 1 will be less than a to the power n. Then the sequence a to the power n will be decreasing. So this I can write, that is not needed, but still, this I can write, this is less than or equal to a to the power n, the whole divided by n plus epsilon divided by 2 into, this is a number which is less than, also a to the power n will be greater than 0 as well, since a is greater than 0 for all n. This I can write n into n plus 1. See, so we are done. 2m. Now see, this is the sequence. Only focus on this thing. You know, if a is less than 1, if a less than 1 and greater than 0 implies a to the power n will goes to 0 as n tending to infinity. So by that you will be getting, which means, and this time n into n plus 1, sorry, n into n plus 1 as well as n into n divided by n plus 1. This goes to 1 as n goes to infinity. So this equals n divided by n plus 1 and is going to 1 and this is going to 0. So product of two convergent sequence will be corresponding limits, provided limits are finite. So this is going to 0. So after certain stage, this quantity will be less than epsilon by 2 for some after some certain stage. So I can write this is less than epsilon by 2 plus, see, this is epsilon by 2 into n divided by n plus 1. This is already less than epsilon by 2. This is epsilon by 2 for n greater than or equal to capital N, capital sum n naught. This n naught is coming by using the fact that this is going to 0, which means this is less than epsilon. That means what we have is that this quantity is less than epsilon. We start with an epsilon greater than 0, then we show that for after certain stage, that means whenever n greater than or equal to n naught, this is always less than epsilon, which means this limit of this sequence is 0. So we are done. So limit of this sequence is 0. This sequence is 0, so limit of this sequence will be f of 1. So answer is f of 1. Is it clear? Any doubt? Please ask. This is the final question from analysis. Now we will be solving some question from linear algebra. That will be around 45 minutes. I will be finishing that within 45 minutes, at most around 40 minutes. Any doubts? Is it clear?
Sir, yes, sir. Proof is clear, sir. Sir, I have one question. How can we cancel that supremum option? Option C. That supremum 0 to 1 fx.
For this, please choose the function f of x equal to minus x. Then you will be able to show that this limit is equal to minus 1, since it is nothing but f of 1. But minus 1 is not the supremum for this function in the interval 0, 1. Because supremum of this function in the interval 0, 1 is just 0. Yeah. Well, so this trick is needed. You need to bring the function in this form. Well, so some questions from linear algebra, many of them are short.
Is this possible to solve this question by approximation of polynomial as the function is given to this as it's continuous on the compact set? Then
you can do that. You can use Weierstrass approximation. First, you need to prove the result for polynomial. Then you will be able to do. Yes. First thing is to show that this is for polynomial you need to show first. Then you need to show that this function, if you are able to find out a polynomial, px converges to f of x uniformly, you will be able to show that n into x to the power n px, which converges to n into x to the power n f of x uniformly. Then you can use the fact that you can show this. For using polynomial also you can show using Weierstrass. This I use some mainly basic definition of integral and continuity. You can try this method also.
Thank you. Yes, sir.
Yeah. So you need to make sure convergence is uniform. One thing I can say, this function will be uniformly convergent. N into x in please verify this should be uniformly convergent. Need to check. Well, So we're going to question from linear algebra. There will be around 4 or 5 questions in 30 minutes. I will try to finish. Yeah. If A is invariant matrix such that A square equal to A, then rank of A equal to trace of A. Is it true or false? Any idea?
True, sir.
True. Someone said true. Yeah, it's true. It's solving. See, there are many ways. You can use the notional projection and many ways, but I am trying to use the here. I am trying to show this using the notion of prime polynomial. See, you are given a it is given that A to the A square equal to A, which means fx equal to x square minus x is an annihilating polynomial. Annihilating polynomial means for any polynomial for which f of a equal to 0. So now use the fact that minimal polynomial is the what is the minimal polynomial of a matrix? Minimal polynomial is the smallest degree monic polynomial for which m of a equal to 0. That is the matrix satisfies that polynomial. So smallest degree polynomial. There are other factors. Other factors are if you are having an annihilating polynomial, minimal polynomial divides always an annihilating polynomial. So mx minimal polynomial mx always divides annihilating polynomial fx, which means roots of minimal polynomials are will be again a root of any annihilating polynomial. So here you are having an annihilating polynomial. So root of this will be a subset of root of this polynomial. But you know root of this polynomials are nothing but what? See, minimal polynomial. I said minimal polynomial is 0 and 1. So this shows that fx equal to some gx into mx. So mx is a factor of fx, but fx is nothing but x into x minus 1. So mx can be what? Either x or m minus 1 or m into m minus 1. So these three possibilities are there only, right? Mx is a factor of fx. So mx can be either x or m minus 1 or m into x minus 1. So now this our minimal polynomial is having only these three possibility. Now case 1, minimal polynomial equal to x. In that case, what will be our matrix? M of a should be 0. M of a should be 0, which means a equal to 0. Oh, sorry. I wrote one mistake. No one pointed it out. Should have. This is not m plus x plus 1 into x minus 1. It was, sorry, m plus 1. Yeah. So first case, in our minimum polynomial is m plus 1. Our a will be equal to then a plus I mx. M of a means a plus I, which is so yeah.
Sir, if x is x minus x.
Fx is
it should be x into x minus.
Okay, sorry. I got this confused with something else. Yeah. Got confused with something else. X. Okay, I missed the question. I went to somewhere. Anyway, now at least you have got some new ideas. So here you need to check the trace whether trace is equal to rank. See, our minimal polynomial possibilities are this. Forget about this thing. This is actually this is for proving something else. we don't need that as for now. Yeah. Polynomial matrix is either x or x minus 1 or x into x minus 1. So in this all possibilities, see, minimal polynomial is a product of linear factors. So you know, a matrix is diagonalizable if minimal polynomial is product of linear factors, isn't it? Since minimal polynomial is in this form, A is, you can say A is diagonalizable, which means algebraic multiplicity of each eigenvalue will be equal to geometric multiplicity of each eigenvalue. In particular, algebraic multiplicity of eigenvalue 0 will be equal to geometric multiplicity of the eigenvalue 0, which means now 0 here algebraic multiplicity, that means nullity equal to number of 0 eigenvalues. Now, what is the rank of a matrix? By rank nullity theorem, rank of a matrix by rank nullity theorem, rank of A equal to n minus nullity of A. Nullity of A is nothing but geometric multiplicity of the eigenvalue 0, which means n minus gm of 0, which means number of 0 eigenvalues, number of non-zero eigenvalues. Is it clear up to now? I'm removing one more step. I can write n minus am of 0. I'm removing, I'm subtracting number of 0 eigenvalues from n, which means number of 0 eigenvalues. Now, see, you see, minimal polynomial is either x or x minus 1 or x into x minus 1, which means possible eigenvalues are any eigenvalue of a matrix is root of a minimal polynomial, and any root of a minimal polynomial is an eigenvalue. By that, possible eigenvalues are possible eigenvalues of A are 0 and 1. That means if matrix is having some non-zero eigenvalue, which will be 1 itself. So the number of non-zero eigenvalue will be just nothing but sum of the eigenvalues, because all possible eigenvalues are 0 and 1. So sum of number of non-zero eigenvalues will be nothing but sum of the eigenvalues. Since only, you can write since only non-zero eigenvalues are 1. So, but which is what? Trace of a matrix. You can write, if you are having a matrix, you can always, there is a relation, there is a result that trace of a matrix is nothing but sum of the diagonal elements of a matrix. That you can show that trace of a matrix is also equal to number of, also equal to sum of the eigenvalues. Please, if you don't know, please prove it. Trace of A. So rank of a matrix is equal to trace of A. Here I have shown something more. I will try to do something more, but this much is enough. You need to know matrix diagonalizable and possible eigenvalues are 0 and 1. Then rank nullity theorem. Then some of the eigenvalues are nothing but trace. Is it fine? Any doubt?
Sir, please can you explain again?
Yeah, well, so we are given a matrix A square equal to A. So which means if you are considering a polynomial x square minus h, that will become an annulating polynomial. Now, you know, if you're having a, you know the minimal polynomial. Minimal polynomial of a matrix is nothing but smallest degree monic polynomial which satisfies the matrix, which means M of A will be equal to 0. Also, there is And other thing is that property of minimal polynomial. If you have an annihilating polynomial, minimal polynomial will be always a factor of annihilating polynomial. So you are already having an annihilating polynomial in your hand, which is nothing but x into x minus 1. So since minimal polynomial is an annihilating polynomial of minimal polynomial is a factor for any annihilating polynomial, so minimal polynomial should be equal to either x or x minus 1 or x into x minus 1. From that, now this much we are having. Now the thing is that this using the from this you can conclude two things. One thing is that A is diagonalizable. Since a matrix is diagonalizable when minimal polynomial is product of linear factors like x into lambda 1, x into lambda 2, x into lambda 3, where these lambda i's are distinct. So whenever minimal polynomial is in this form, it will be matrix is always diagonalizable. That we are getting if we are having something like square. Matrix won't be diagonalizable. So please, if you don't, please note verify these all properties. This is our property. These are the things related to polynomial. I'm not proving all this thing, so it will take more time. And other fact is that given any eigenvalue, that eigenvalue will be a root of minimal polynomial. And converse is also true. If lambda is a root of minimal polynomial, then lambda will be an eigenvalue of the matrix. So for getting an eigenvalue, it is enough to look at the roots of the minimal polynomial. See, only three possibilities we are having. So from this, you will be getting the all possible cases for the eigenvalues, which are nothing but 0 and 1. So our eigenvalues of matrices are the subset of the matrix 0, 1. If matrix is having eigenvalue, it should be 1. Now we know matrix is diagonalizable. By diagonalizable, what we mean? Algebraic multiplicity of any eigenvalue is equal to geometric multiplicity. In particular, this I mean algebraic multiplicity of the eigenvalue is 0. That means how many eigenvalues are there. So which will be equal to geometric multiplicity. That means geometric multiplicity of the eigenvalue 0 is nothing but dimension of null space of A. That means nullity. Rank theorem I get the rank of A equal to n minus nullity of A, which is nothing but n minus geometric multiplicity, which is nothing but n minus algebraic multiplicity, which means I am subtracting number of zero eigenvalue from n. That means total order of the matrix, which means I am getting number of non-zero eigenvalues. But see, we are only having our only possible non-zero eigenvalue is 1. Then which will be equal to number of eigenvalues. But number of eigenvalues nothing but trace of A. Here we have made a lot of result from diagonalizable, minimal polynomial, rationality theorem, some of the eigenvalue equal to trace. So in this problem looks very easy, but we have used a lot of ideas. I have shown all the ideas, things that you have studied in your class. Is it clear now?
Yes, sir, it is clear.
Yeah. Mainly I have properties. There are other methods also. Yeah. So this problem, let A be a 3×3 real symmetric matrix such that A to the power 6 equal to I. Then what can you say about A square equal to I? Is it true or false? Anyone?
Is it true?
True. Yeah, it is true. So how can we show? See, A is a real symmetric matrix, first of all. If eigenvalues of real symmetric matrices are always real. Since, please, if you don't, please show this, please convince yourself. You might have studied. Since A is real symmetric, eigenvalues of A are real. Now see, you are having an, we have A to the power 6 minus I equal to 0, which means fx equal to x to the power 6 minus 1 is an annihilating polynomial. I think there are two ends. Yeah, please make sure this will. So, you know, annihilating polynomial. So once you have an annihilating polynomial, you will get some possibility for minimal polynomial. See, I said that minimal polynomial divides any annihilating polynomial, which means minimal polynomial is a factor of annihilating polynomial. So mx divide x to the power n minus 1. This we are having. See, and another thing is that root of minimal polynomials are nothing but eigenvalues. Now we know that our matrix is having, since matrix is real symmetric, eigenvalues, all possibility of eigenvalues are all reals. So mx will be having only real eigenvalues. But that means root of minimal polynomials will be real. Matrix will be having real eigenvalues, which means root of minimal polynomial will be real. What are the root of this polynomial? What are the roots of this polynomial? One, these are roots of this polynomials are nth root of 6th root of unity. So it is having only two real eigenvalues, 1 and minus 1. Other eigenvalues will be complex. So has only two real eigenvalues, which are 1 and minus 1. Others, all other eigenvalues are 0, complex numbers. So since mx is having also real eigenvalues, mx can be, then mx can be m plus 1 or m minus 1 or m into m plus 1 into m minus. Also note that these eigenvalues are of multiplicity 1. So minimal polynomial can be one of them. Is it clear? Once this much is done, problem is almost done.
Yes, sir.
Is it clear? Yeah. So we are having this much possibility, which means what? Since these are the possibility of minimal polynomial, in each possibility, in case one, in this case, you will be having, just a second. Yeah. In this case, you will be having a plus I equal to 0. In this case, you will be having a minus I equal to 0. This case, you will be having a plus I into a minus I equal to 0, which means here in all this case, please verify, in all these case, you will be getting a square equal to I. Take I in the right hand side, and you will be getting a square minus I equal to 0. So in all this case, you are getting a square equal to I, which means this is true. Is it clear? Any doubts? Oh, no. Okay, well. Yeah. Another question. The set of nilpotent matrices in M3R spans M3R considered as R vector space. It's a kind of interesting question. What do you think? Is it true or false? Span of nilpotent matrices. You are having a vector space M3R over R. Then you are taking a subset of that vector space, which consists of all nilpotent matrices. Question is, well, what will be the span of that subset? Question is,
I think it is true, sir.
It is true. Yeah, let's see. I'm taking a matrix, arbitrary matrix from M3R. Let A belongs to M3R. Some 3x3 matrix, some arbitrary matrix. What do you mean by span of nilpotent matrices? Some finite linear combination of nilpotent matrices, which means if span of nilpotent matrices is M3R, I should be able to write A as some finite linear combination of nilpotent matrices, which means A should be in the form some C1 N1 plus C2 N2 plus etc. plus Cm Cm. I'm using M. Cm mm, where Ci's are real numbers and Ni's are nilpotent. What do you mean by the nilpotent matrices? Nilpotent definition is nothing but A to the power n equal to 0 or some n belongs to natural number. For some n belongs to natural number, if you are getting A to the power n equal to 0, then matrix is called nilpotent. Now, what can you say about the trace of an nilpotent matrix? If a matrix is nilpotent, trace of an nilpotent matrix is always 0. This you can show in many ways. One way is that eigenvalues of an nilpotent matrix will, please note that I'm saying something, some result. Eigenvalues of nilpotent matrices are only 0. Now we know that trace of a matrix is nothing but sum of the eigenvalues. One of the definition, one of the property, not definition. Definition is some of the diagonal elements. So some of the eigenvalues will be 0 for a nilpotent matrix. So trace of a nilpotent matrix is always 0. Other ways are also there. You can show using this also, and using the fact that trace of AB equal to trace of BA and all. So trace of a nilpotent matrix is always 0. So if you have also trace function is trace of, also trace of A plus B is nothing but trace of A plus trace of B. And other properties that trace of some scalar into A is nothing but A into trace of A. Trace is nothing but some of diagonal elements. So using that, you can show these things. Now coming to this, if you are able to write in this form, what will be the trace of A? Trace of A is nothing but trace of
0.
Yeah, 0 exactly. C1 N1 etc. Cm Nm. This is nothing but C1 into trace of N1 plus etc. plus Cm into trace of Nm. But all trace of Nas are 0 for all I, which means this is equal to 0. That means we are getting for any linear combination of nilpotent matrices, the trace of that linear combination is always equal to 0. Which means if you are taking a matrix like whose trace is not equal to 0, like ideal matrix particular. If you are taking ideal matrix, trace of A will be equal to n. So that cannot be written as linear combination of nilpotent matrices, which means this span of nilpotent matrix is not equal to M3R. So this is false. Fine. See, I have used many property related to trace and sum of values equal to trace. Please prove this if you haven't studied this. Prove. Okay, well. Question. Yeah. We are having a vector space. V is an n-dimensional vector space. Just a second, 37. You are given an n-dimensional vector space. T from V to V is a linear transformation such that rank of T is less than rank of T cube. Then what can you say about this? Then which of the following statements are necessarily true? Null space of T equal to range of T, null space of T intersection range of T equal to 0. There is a non-zero subspace W such that intersection of null space and range equal to W, then null space is contained in range space. What do you think? Okay, since lack of time, I'm solving this for last two problems. See, you are given that rank of T is less than rank of T square. Given rank of T is less than or equal to rank of T cube. Now note that range of T cube is contained in range of T. Right. I'm using the notation R. Image will be better. Image of T is contained in image of T cube. That means dimension of this. See, but rank of T is, oh, I brought mistake again. Range space. Is it fine? Which means by if y equal to T cube of X, then y is nothing but again T of T square of X. Which means if an element is there in range of T cube, it will be there in range of T as well. But by this, what we can say is that range is a subspace of range of T cube is a subspace of range of T. By this, we can say rank of T cube is less than or equal to rank of T. But it is already given that you are already having that rank of T is less than or equal to rank of T cube. By this, you can say rank of T equal to rank of T cube. So this much we are having. Now, which means what? Nullity. By rank nullity theorem, you can show that nullity of T is nothing but nullity of T cube. But there are null space. For null space, I'm using some shorter notation. For null space, I'm using N of T. For range space, I'm using R of T. So we know. You can show, please prove this. Null space of T will be contained in null space of T square will be, and this is again contained in null space of T cube. This is very easy. If you are taking one element from null space of T, it will be then for that element. If X belongs to null space of T, then Tx will be equal to 0. Then T square of X will be against 0 because T square of X is nothing but T of T of X. Similarly, T cube of X will be 0. So this you can easily verify. Now, see, in particular, null space of T is contained in null space of T cube. So what you are having is that null space is a subspace. Null space of T is a subspace of null space of T cube. This is a subspace. Also, dimension of these two vector spaces are equal. So in that case, null space should be equal to null space of T cube. Please prove this. If you don't know, if you are having a subspace, dimension is equal to the vector space, then those two vector spaces will be equal. Now see, null space of T and null space of T are equal, but null space of T square is a subspace in between these two subspaces. So from this, from one I can write null space of T is nothing but null space of T square. So for the given things, I showed that null space of T equal to null space of T square. Now this is needed for showing B option. So the answer of this question is B. Now if you're taking an element from null space of T intersection range of T, like I'm taking, let X belongs to N of T intersection R of T, then which means what? Tx equal to 0. Also there exists Y such that X is equal to Ty. That's what I mean by saying X belongs to range of T. See, X is equal to T of Y, which means if you are applying T on this both side, T on both sides, you will be getting Tx will be equal to T square of Y. But you know Tx is already 0, which means 0 equal to T square of Y. But which means what? Y belongs to null space of T square. But that is nothing but null space of T square and null space of T are same. Which means T of Y will be equal to 0. But our T of Y was nothing but X. Which means X equal to 0. So if you are choosing an element from intersection of null space of T and range of T, that elements become 0. So option B is true. So main trick is to use prove this thing. Is it fine? Any doubts? Any doubts?
Clear, sir.
No. Okay, well. Yeah. So it's the final question. The subset Gn of GNR of MNR consists of all invertible matrices is dense in MNR. Which means, is it true or false? Actually, this is true. I'm showing. We need to show that closure of dense means GNR is dense in MNR means we need to show that closure of GNR in MNR is MNR itself. That means the union of GNR as well as its limit point should be equal to MNR. We need to show that closure. I'm just using this notation. GNR closure equal to MNR. Closure for union of GNR as well as its limit point. So if you are taking GNR means and closure of all invertible matrices. So in closure, definitely GNR will be there in GNR closure. So you need to take a non-invertible matrix which is not invertible, matrix which is not invertible, then you should show that that is a limit point of GNR. So it is enough to show that it is enough to show that any non-invertible matrix is, say, limit point of GLNR. Which means if you are taking a non-invertible matrix, let A belongs to MNR is not invertible. So in order to show that A is a limit point of GLNR, you should be able to find out a sequence of matrices from GLNR which converges to A. That means sequence, if you are able to show that there is a sequence of invertible matrices which converges to A, then you can say that A is a limit point of GLNR. This is one method, one of the equivalent criteria. There are other things like every neighborhood has infinitely many points from GLNR. Both are equivalent. So I'm using that sequential criteria. So consider this sequence. Before that, I have taken a non-invertible matrix. So which means this matrix will be having an eigenvalue 0. Let the eigenvalues of A be. Let the eigenvalues of A be lambda 1, lambda 2 up to lambda n. Now consider A plus 1 by n of I. See, please note that, please verify, if you are having a matrix A, if you are having a polynomial P of A, you might have studied, then if eigenvalues of A's are lambda i's, then eigenvalues of P of A will be P of lambda I. So here also it is in the form of P of polynomial, like x plus P of A you can consider to be x plus, this you can relate with the x plus 1 by n. Yes. So the eigenvalues of this matrix will be nothing but lambda I plus 1 by n. Then eigenvalues of A plus 1 by n I are lambda I plus 1 by n for I equal to 1, 2, 3 up to n. Fine. Now see, a matrix is invertible if all the eigenvalues are non-zero. So can I say that this lambda I plus 1 by n is non-zero after certain stage? So I'm claiming one thing. Lambda I, there exists n naught belongs to natural number such that lambda I plus 1 by n not equal to 0 for all n greater than or equal to n naught. Please verify this. See, for example, I am saying one hint. See, all these things, lambda I plus 1 by n goes to converges to lambda I. Yeah, if you are considering a complex plane, so suppose it's lambda 1, lambda 2, this lambda 3 is 0. If lambda 3 is 0, then 0 plus 1 by n is always non-zero, like lambda n, something like that. Then if you are choosing a circle which doesn't pass through 0, like we are choosing a board, center lambda i's. Then since lambda I plus 1 by n goes to 0, you will be able to find a stage like some n naught. After that, this lambda I plus 1 by n will be inside this, which means this is non-zero. For this also you will be getting some, this you are getting for some, for her you are getting some n dash, for her you are getting some n1, for her you are getting some n2. Then choose n1 to be maximum of n1 and 2 in that way, and nn. Then you will be getting an n1 such that after certain stage, this lambda I plus 1 by n will be inside this all these circles. I'm giving a rough proof, which means this is lambda I plus 1 by n is non-zero after certain stage, which means when n greater than or equal to n naught. So that means A plus 1 by n is invertible for n greater than or equal to n naught. Which means since it is having non-zero eigenvalues. And note that A plus 1 by n converges to A as n tending to infinity. How can we say? Here I need to use the notion of no. So here you are showing some, you are saying some convergence. This is not real numbers. You need I don't know whether all of you have studied notion of no. Here I'm taking no. You know, for Rn, elements from Rn, you define distance, absolute value, distance of A to A minus B to be square root of A if we are having A1, A2 up to AN, and if we are having another n people B1, B2 up to Bn, then distance between these 2 points will be square root of An minus Bn whole square plus B, A2 minus B2 whole square plus up to N minus Bn whole square. So in that way, you can define norm of A minus, no, distance between A minus B to B. Here I'm using the term norm. This is nothing but square root of summation ij from value to 1 to n modulus of Aij minus Bij all square. So under this notion, modulus of A plus n minus A will be nothing but A plus A by n I into I. A plus 1 by n means A plus 1 by n into I. This is nothing but 1 by n into I. Norm of this is nothing but, you can take 1 by n outside. Norm of I. Norm of I means I minus norm of I minus 0. Using this definition, you will be able to show that this is nothing but square root of n divided by n. This is nothing but n divided by square root of 1 divided by square root of n, which goes to 0 as n tending to infinity, which means A plus 1 by n I converges to A as n tending to infinity. So you are getting a sequence of invertible matrices. That means if you are choosing sequence Bn to be A n naught A n naught plus 1 A n naught plus 2 in that way. These elements of the sequence Bn are invertible matrices. Also you can see Bn converges to A. Bn is nothing but the subsequence of the sequence. Bn is nothing but subsequence of the sequence A plus 1 by n, where n varies from 1 to infinity. So I'm chasing a subsequence. So you are getting a sequence of invertible matrices which converges to A. Since A plus 1 by n converges to A, Bn will be again converges to A since it has subsequence. It means A is a midpoint of G1. So subset GLNR of MNR consists of all invertible matrices is dense in MNR. So is it any different doubt? Is it clear? But I don't know all of you whether all of you have studied the notion of no, but so it's defined. Just remember this definition if you have studied the definition of norm in matrices. Is it clear? Any doubts?
Clear, sir.
So there are many things to prove. If A is an eigenvalues of A is lambda is eigenvalue of P of A is P of lambda I, those ideas I'm using. Yeah, well, okay then. That's all. I'll be sharing this PDF as well. If you're having any doubts related to some problems that I did, you can ask.
Thank you, Balu. Thank you for this wonderful session with lots of good problems from the previous question papers. I'm sure that any serious student who attended carefully will definitely get benefited out of this session. Now it is time for interaction.
Yeah.
Balu, you can turn off your presentation and keep your video on.
Yeah, I will be.
So, dear participants, now it is time for interaction. Please introduce yourself before making comments. Yes.
Hi everyone, my name is Nivya Sabu, a third year graduate student, BSc student from Kerala. So I would like to thank Dr. Vinod Kumar sir for organizing such a wonderful problem solving section. I believe that this was a great opportunity for all those TIFR aspirants. Also, I would like to express my sincere gratitude to Balu sir. Sir, we are very grateful for the effort and time you took to prepare this section. And thank you so much, sir, for spending this time with us. And also, I just wanted to thank my sincere gratitude to both of Vinod Kumar sir and also to Balu sir. Thank you so much, sir.
Sir, I am Shikha from Birla Institute of Technology, Meshra, Jharkhand. I'm a second year M.Sc student. Sir, your session was really very nice. You explained each and every question in a very well-defined manner, and the proof was really very easy and understandable. So I think this session will be very much helpful for the TIFR aspirants. Thank you, sir, for taking time for us, and thank you, Vinod sir, for organizing such sessions. Thank you, sir.
Yes.
Hello, sir. Sir, I am Dia. I am from IIT Guwahati, MSc third semester. I am also preparing for TIFR GS. Sir, please give some trick. I mean, what is the strategy to solve the true and false questions?
Can you repeat, please? What is
Sir, how to solve the true and false questions?
Yeah,
Balu, she is asking for
how to solve true or false question.
Any tips regarding the
the thing is that it is always better to know a lot of techniques to attack a problem. If you are having that idea, like if I am choosing the uniform continuity, there just apart from that definition, external definition, if you know the minimal property of that function, like under certain condition function will become uniform continuous and all. If you know a concept in a very detailed manner, like with knowing many examples and many properties, and then by looking at the question itself, you will click the idea. Oh, it will go like this, it will go like this. So it is always better to know more content, more concept related to one fixed topic, like I said, uniform continuity. So, and other thing you can eliminate for question, you need to know something more details. You won't be able to eliminate things easily. So if you ask like that, I will always say, when you study some concept, you try to know a lot of examples and a lot of properties related to that concept. Like one thing I can say, if a function, if derivative function is bounded, you can show that a function is uniformly continuous. This is one thing. If you are given a function like f of x is equal to sin x, if you are in this easy question, it is asked that whether it is uniformly continuous or not. If you know something more, you can easily answer immediately. So you need to know more concept than that you use to solve these option questions with some options, multiple choice. So it is like kind of descriptive, you can say, and kind of writing. There you need to know more concept.
Let me add one. Yeah, let me add one point from my side. See, while learning, make it a habit that analyzing the concept in detail and look at some very careful about the hypothesis in the theorem, and see whether what happens if something is reduced or relaxed. So give special attention to counter examples. Then that will be very useful to conclude some, concluding. In order to conclude something is false, an example is enough. So that is very, if you know with lots, if you are available with good number of examples, I think you can easily easily analyze the question and conclude to the answer.
Yes.
Thank you, Diya.
Thank you, sir. Thank you, sir, for today's session. It is very good.
Yes.
Good afternoon, sir.
Good afternoon, sir. I am Dharmendra from.
Yeah, 1 minute. Yes, yeah, Dharmendra, you just
I am Dharmendra Singh from BARC Visakhapatnam, doing library job in BARC. I am doing mathematics myself also, and by watching YouTube video and search video. This session was very useful and detailed. I enjoyed it. Sometimes I did not got clearly, but I enjoyed it. I want to know how to clear GS, TIFR GS interview. Because I cleared once exam in 2009, but I did not clear my interview in CM Bangalore. I want to know your research experience also, and some reference book also.
Reference book. Okay. Reference book, I can suggest a book. For interview, things that you need to know concept more than techniques or shortcuts. So whenever, as I said before, as Sir said also, whenever you study some concept, try to learn it in a more detail with more examples, counter example, more properties. So that kind of thing will be giving you, will help you to clear interviews. So interviews, they will be asking method of solving, like proof. They will be asking question based on proof. Whatever you are saying, they will ask, how is it possible? So you should be ready to answer each and every claim that you are making. So whenever you study something like during interview, like if you're saying during interview, since I solved some problem, there I used composition of two uniformly continuous functions is uniformly continuous and square root of x is uniformly continuous. It's not just something. So there they may ask proof also. So you should be ready to say proof of all the things that you are saying. So basically it is about studying things in very detail. And other thing regarding suggestion of book for real analysis, I can suggest some books. There are some books called Problems in Mathematical Analysis by 𝕨𝕨 and Koser. You can search it in internet, you will get it for free. Those books, you can find a lot of problems with a lot of different techniques. If you're studying 𝕨 theorem, you will be getting a lot of problems under that section. So you will get many ideas and you will get to know many properties related to 𝕨 theorem. So those kind of, that book I have found it very nice. Then for linear algebra, I have seen there is a book called Challenging Problems in Linear Algebra by Fossen and Sang. So you can try that book. That book is also consists of a lot of problems by topic wise. So those kind of some problem oriented, some concept oriented book will help during these interviews. And mainly it is studying concept in detail. Also, during interview, one thing you need to know, never use any shortcut. Never ever use any shortcut during interview. If you're using some shortcut and if you're telling, I don't know this proof, I just know this result, then that may create some bad impact as well. So try to avoid shortcut. If you're using some shortcut, you should be able to do that. So these things will help. Yeah.
Okay, Balu, it will be good if you can include that reference names in the PDF that we will share. This class notes.
Yeah, I will write these two books name in the PDF before sharing.
Yeah. That will be good. Okay, thank you, Dharmendra Singh. Others?
Hello.
Yeah. Nishita.
Hello.
Okay, Nishita. I should have please. Yeah. Yes, Nishita.
Hello, I'm Nishita from Maharashtra. Thank you so much, sir, for today's session. Your lecture was just amazing, and the style, the way you were explaining everything, each and every terms was just means very amazing. And I'm very thankful to Vinod sir also for connecting you with us. And thank you so much.
Thank you, Nishita.
Welcome.
Yeah, Aishwarya, you can.
Hello, sir.
Yeah, Meenu, yes.
Sir. My name is Meenu and I'm third year BSc student from Kerala. First, I thank Vinod sir, our guardian of Math Aspirants group, to arrange this wonderful section to me and my friends. And also, I thank Balasubramanian sir to give more effective method and tricks to solve a problem. Once again, thank you, sir. Thank you so much.
Welcome.
Thank you, Meenu. Yes, Aishwarya, you can speak.
Sir, my name is Aishwarya Dhalwal. I'm from Maharashtra. I'm just apply. I just fill the form for TFR. So this session is very useful for us. And thank you so much. Such a wonderful session. And I want to thanks Vinod sir to arrange such kind of session. And thank you Balu sir also, because they explain each and everything very nicely and very easily. It is very easy to understand. So thank you, sir, and wish us luck so we can go for a TFR and enjoy and take a experience of that. Thank you, sir. Thank you so much.
Definitely, Aishwarya, you can win. Attend the exam with all the confidence.
Okay, sir. Okay. Thank you.
Yes.
Hello, sir. Good afternoon, sir. I am Gauri from St. Teresa's College, Kerala. I really enjoyed today's class, sir. It was thank you for sharing your valuable time and knowledge with us. It was really a great experience for us. And secondly, I thank Vinod sir for arranging such a great class for us. Thank you, sir. It was really worth the time. Thank you, sir.
Sir, my name is Arya. I'm third year BSc Math student from Calicut. First of all, thank you so much, sir, for this nice section. And you explained every question very clearly, and it's really helpful to us. And thank you, sir.
I'm Anandi. I'm BSc Math third year. I'm studying BSc Maths third year from Pondicherry. Thank you, sir. Thank you, Vinod sir, for organizing a wonderful session. Thank you, Balu sir. Today's session was really helpful for us. Thank you, sir. It's make to understand better, sir. Thank you, sir.
Yes, Didi.
I want to thank for this today's wonderful session, and you cleared all the concepts, and it helped us to revise all the theorems and proofs, and you also shared your knowledge with us. So I want to thank once again for spending your valuable time with us. Thank you so much, sir. And also I want to thank Vinod sir to arrange these kind of sessions. Thank you so much, sir.
I'm Gopika, third year BSc Math student from 𝕬𝕤𝕦 Guwahati College, Kerala. Today's session is really nice. You explained each and every questions really well. So it is easy to understand, and it will be really helpful for our preparation. Thank you so much, sir, for your time and effort. And also thank you so much, Vinod sir, for organizing this session. And thanks, sir.
Hello, sir. I'm Malavika, third year BSc Maths student of 𝕬𝕤𝕦 Guwahati College, Kozhikode. Thank you so much, sir, for this wonderful session. The class is really nice and it is really helpful for us. We really enjoyed it. Thank you so much, sir, for your time and effort. I would also like to thank Vinod sir for conducting such a wonderful session for us. Thank you, sir.
So I'm Anamika. I'm also from 𝕬𝕤𝕦 Guwahati College, Calicut. Thank you, sir, for the session. The well-prepared session. It was very clear questions, and thank you so much, sir, for the session. And can you refer that name once more, and can you post that name of that?
Yeah, I will be sharing.
For reference.
Yeah, I will be sharing. Yeah.
So my name is Abarna Lal. I'm a graduate student and I'm preparing for TIFR and IIT JAM. And today's session was very nice. And thank you so much, sir, for giving us your valuable time. And it was very informative, and the concepts which you told us was very good. And also for the tips. And Vinod sir, I really thank you for organizing this wonderful session. So thank you so much, sir.
Yes.
Myself Shilpa. Today's class was really nice. Came to know about more varieties of problems, and you also provided us with tips for solving true or false question statement type problems. And it would be very useful for many of us for
upcoming exams. Thank you, sir. Thank you, Vinod, sir.
Can you share, sir, research experience, your research experience?
Different. Yeah, research it is somewhat different from what you study in M.Sc. There you need to do something that there you are doing something that you have that is not yet done. That is not yet done. So it is good. You should have some like you need to work hard and some motivation. You need to learn many things. You need to do a lot. You need to apply all the tricks that you learn to solving a new problem. So in short, that much I can say. Once you get into PhD, you will get to know. But it will be entirely different from how you used to do in school and college.
I am Anjana from St. Teresa's College, Ernakulam. I am a final year BSc Mathematics student. Today's session was really very helpful. We came to know in detail about how to solve the different types of problems, and the concepts were made very clear. Thank you for spending your valuable time for us, and thank you, Vinod sir, for organizing this session. It was really very helpful. Thank you.
My name is 𝕬𝕤𝕦𝕤. I am from TMG College, Malappuram, and your class is very nice. It is really amazing and helpful. Actually, I got very little part due to the problem of internet, but I will I will hear its recorded session. And thank you, Vinod sir, for conducting this section. I am Lakshmi. I am from CMC College, Tirur, Kerala. Today's class was really nice, and you explained each topic very clearly. And thank you, sir, for spending your valuable time with us. And thank you, Vinod sir, for conducting this class. Thank you.
So let us wind up here. Thank you, Balu.
Okay. Thank you.